All right, so this is part two of this using the ideal equation of state ALEKS topic. In part one, I solved a much simpler type problem. So if you're stuck on the simpler version, definitely check out that video first, but this is definitely probably the version that's going to give people the most trouble. It's a little bit more complicated. We're gonna have to do a lot more steps essentially, but we'll get through it. So the first thing, of course, is we're gonna want to organize the information that's given, try to break down what these words are really saying, maybe try to visualize it, and then obviously put it all together. So the first thing that I'm gonna be looking at here is what the question is. A chemical engineer must calculate the maximum safe operating temperature. That's what we're looking for, is a temperature of a high pressure gas reaction vessel. So I might sort of highlight this temperature, put a question mark there if that's what we're looking for. The vessel in question is a stainless steel cylinder, so that's going to be an important piece of information, that measures 60 centimeters wide and 72 centimeters high. So I'm going to write cylinder, and my width equals 60.0 centimeters, and my height, or it is high, as 72.0 centimeters. So using this information, I'm going to be able to figure out what the volume of that cylinder is. So anytime we're thinking about this ideal gas law, we want to be thinking about the volume. So even though we're not given a volume, we're given a way to figure out what the volume is. So I'm gonna start with that, and then I'm going to move on. I'm going to figure out the other pieces of information. The maximum safe pressure, so here we're going to be talking about pressure, inside the vessel has been measured to be 6.5 megapascals. Pretty annoying that they're giving us the unit of pressure in terms of megapascals, but in different industries, there's going to be different standards, and it is very common that we're going to be using different units, so we need to get comfortable with those as well. So 6.5 megapascals, that's going to be my target pressure, or my highest pressure. For a certain reaction, the vessel may contain up to 37.9 kilograms of sulfur hexafluoride gas. So this is going to be related to the number of moles, but for right now, I'm just going to write 37.9 kilograms of SF6. That's going to be the other, another piece of information. And then it says calculate the maximum safe operating temperature the engineer should recommend for this reaction. So again, we're going to be thinking about pressure, we're going to be thinking about moles, volumes, temperatures, obviously. So this to me is telling me PV equals nRT. Round your answer to 3 significant figures. So before we can start plugging things in, we need to sort of translate this information into a volume, this pressure information into a pressure that we're used to using, and this number of kilograms into a number of moles. So let's go ahead and get started with that. For this cylinder, what I actually did is I just Googled cylinder volume equation. I think that's the term that I used, cylinder volume equation. And I found that for the volume of a cylinder, the equation is pi times r squared times the height. So this equation here, we can use with this information over here to figure out what that actual volume of that cylinder is. So pi, we know we can just plug in 3.14. For r, now this is the radius. It's not the entire width, it's the actual radius, so it's going to be half of this. 30 squared times 72. So my answer here is 203,575 centimeters cubed. So I have to pay attention to my units. I've got centimeters, so centimeters squared times centimeters would be centimeters cubed. And I know that 1 centimeter cubed equals 1 milliliter. So this would be another conversion that you could do if you weren't familiar with that, or you weren't exactly sure. Just check on Google, see what it says. What is 1 centimeter cubed into milliliters? So this would equal milliliters, and then we could go ahead and convert that to liters, right? We want to have our volume in liters for PV equals nRT. So 203.575 liters. That's good. So that's step one. With this megapascals, I would do the same thing. When I was doing this problem, I literally just went into Google, said 6.5 megapascals to atmospheres, and it told me that pressure is actually, where did it go? 64.15 atmospheres. So that would be just one way to do that conversion. And I think when you're doing ALEKS, I think that that's a good strategy. You do want to be able to do those conversions, right? If I gave you the conversion factor, you might want to look up what 1 megapascal to atmospheres is, and then use that conversion factor to confirm that this is the right pressure. But I think when you're doing problems like this, that's a totally valid way to do those conversions. That's what I would do. Next, we've got this 37.9 kilograms of sulfur hexafluoride. I'm going to want to convert that into moles. What's the number of moles that should be? So 37.9 kilograms is going to be 37,900 grams. And I'm going to use the molar mass to convert that number of grams into number of moles. So I know that 1 mole is going to be 146.07 grams, so that's what we used in the previous problem, so I didn't have to calculate again, which is convenient. And then this gets me to a number of 259.47 moles of gas, of that, what is it, SF6. So now we've got moles, atmospheres, and liters. We've basically converted all of our sort of different information into the proper units for us to use PV equals nRT. So now we can go ahead and plug it in. So my pressure is going to be 64.15 atmospheres. That's the correct unit there. My volume is going to be 203.575. And you'll notice that I haven't rounded any of my numbers yet. So in a problem like this where we've got a lot of different conversions, a lot of different things going on, you really want to carry all of your digits until the very end, right? Each one of these calculations, if I'm rounding my answer, then by the end I'm going to have a significantly different number than if I carry all those digits. And so when we're doing calculations like this, carry all of your digits until the very, very end. So 203.575 equals my number of moles, which is right down here, 259.47, times my R value, which is again going to be that 0.08206. Maybe I'll just write that right over here. Typically, I'm just going to write R just to be a little bit lazy there, I guess, instead of having to write out that whole thing. I guess I wrote it there anyhow, but you get the idea. Now we can solve for T. So I've got one equation, only one unknown, this R value obviously right there. And I can solve this for T, and I get a value of 613.3 Kelvin. So make sure you're paying attention to your units. And I'm being asked for the proper temperature in degrees Celsius, so I'll just convert this to Celsius. And round your answer to 3 sig figs, gets us to 340 degrees Celsius. That is the answer that I calculated here. That's what I put in, and I got a good green correct symbol. So that's basically it. If I want to take a step back, right, and just review this really quickly, we're given a lot of information, and we're asked to find what the temperature is going to be that's going to stop, right, that's going to stop the pressure from going higher than 6.5 megapascals. If I continue to increase that temperature, then this pressure is going to be higher than 6.5 megapascals, which is too high, right? We want to limit the pressure in this problem, in this cylinder, to 6.5 megapascals. This is going to be the maximum temperature that will, get to that pressure, but not go over that pressure, and that's what we're looking for. All right, hope that helps.